thank you all for coming to the first talk. I know it's very early in the morning, 9 a.m., but thank you all for coming. Today I'm going to present on our work on morphophonology, and well, in this work we examined complex motion events in Turkish Sign Language, and we also looked at age of acquisition effects, and we used computer vision to investigate that. I'm going to share our results with you for this particular study. Before I start this presentation, there are people I would like to thank for. Demet, Ayşe, and of course our participants. They were very helpful. Okay, so I'll start by defining what a complex motion event is. Well, in any event, there could be a path and there could be a motion, right? And we call this motion manner, the manner in which the event is done, right? And natural languages have different ways of, encoding this information, producing this information. So here we have an example video. Let's watch it. Including a cute dog. Maybe you like it. So cute, right? So because the dog is cute, I'm going to play it again, so we can appreciate the cuteness. Right, okay. Not the third time, though. But I can share the slides if you're interested in the dog. Okay, so here in this event, let's describe what's going on, right? So there is like a path. The path could be like a circle, going in a circle. And there is also motion, limping. The dog is limping, going on one foot, right? So events can have both components, path and manner. And languages have different ways of encoding this information. We looked at this in a sign language. And the question is this, right? How do sign languages encode this information, basically? Well, we have observation for ASL, American Sign Language. So let's say what researchers say about this. For example, Supala says that there are restrictions on complex events. For example, certain classifier handshapes require the sequencing of manner and path. So you don't do it simultaneously, but you basically sequence different information. You first say the manner, then you say the path, as in this example. Right? So the example is a person running zigzag uphill. The person is signing manner first in ASL, and then the path, so sequencing information. This is possible in ASL, and this is the dominant approach, right? But others also can conflate both forms and produce simultaneous forms of manner and path, as in this example. A human agent walks in a circle, so you can basically do this, indicating both path and manner at the same time, simultaneously. We call this conflation, or conflated forms of more complex motion events. And interestingly, there has been reported by, Slobin and Hoyting reported in 1994 that a mixed form is also possible, separate from, conflation, conflated forms, and sequence forms. So what's a mixed form? A mixed form is like this, as in this example, example 3. So you basically, I'll give you some time to look at the example. Maybe we can discuss after that. Here, as you can see, the signer first signs the manner, the action of running, right? This is the manner. And then in the second time, they use a conflated form, simultaneous signing of manner and path together. So we call this form a mixed form. Why mixed? Because it mixes both sequencing and also conflation, conflated forms. A rough translation of the sentence could be that a man runs into a house, right? What about Turkish Sign Language, the language that I am interested in, we are interested in this study? So Turkish Sign Language also is reported to use all these strategies, and we discovered in the study. Just to show some examples, right? So here, this is an example. Example 4 shows sequential form used by the signer. So you'll see here separate signs for manner and path. Let's watch it. This is in Turkish Sign Language. And this is the gloss. So let's go one by one. So first, the signer does women. This is women for Turkish Sign Language. And then you see the manner, right? Walking on toes, the manner of the event. And then there is a separate path, right? So this is clearly sequential. So this can be one example of sequence forms in Turkish Sign Language. And we can also have, like in ASL, conflated forms as in a single sign. This information can go to the same sign. Let's watch this. I think, yeah, it's clear from the video. So again, women and then conflated form. But this is the gloss. And we also observed the use of mixed forms in Turkish Sign Language, meaning that they use the combination of both. So first manner, and then doing them simultaneously, right? Walk on toes, manner, and after the manner, they also conflate the forms and produce manner and path together, which is interesting. So these were the expressions that we were interested in this study. To reiterate, we were interested in sequence forms, mixed forms, and conflated forms. Some background information, right? Özgürek et al. 2015 looked at Turkish home signers and Turkish hearing speakers and examined, the production of path and manner as in these forms, conflated, sequence, and mix. So I would like to highlight the second part of this plot, as in here. So they looked at the production of both manner and path in Turkish home signers. By home sign, I mean the parents are hearing and children are deaf, and between the parents and the children, there is a communication language system created, which is not a natural sign language, but it is a way of communication, right? So they looked at how home signers actually encode this information, and a clear difference is that, well, home signers produce a lot more conflated forms than ASL signers, so they conflate path and manner information more. And they also, interestingly, home signers, according to this study, they also use mixed forms, so they mixed path and manner. So they use a sequence form and then they use a conflated form. And Özgürek et al. Says that this is like an intermediary step to sequencing, to structure, basically, from more, because, conflated forms are more iconic in nature. The meaning is very transparent. But when it comes to sequencing or sequence forms, it's more structural. And in this study, we are also interested in age of acquisition effects. So what do I mean by age of acquisition effects? Well, as most of you know, almost 90% of all deaf individuals are late signers, meaning that they are born into hearing parents or non-signing parents. And late signers receive, unfortunately, don't receive frequent and regular input until they start formal education, say pre-garden, kindergarten or preschool or any deaf school. Then they start typically receiving frequent input. Not valid for all late signers, but some of them definitely don't receive frequent exposure to their first language in this environment. So we are interested in what happens to late adult signers that experience this language delay, let's say, first language delay. And from the literature, we know that late signers may exhibit certain age of acquisition effects. For example, we observe differences in morphosyntax compared to native signers, that is, signers born into deaf parents and acquire sign language natively. For example, difference in morphosyntax, intentional processing, lexicon, pragmatic abilities. We have some studies, Kadir and I, on pragmatic abilities, lexicon as well, and also some spatial language development. We observe some differences, like literature observes some differences. So what about our research questions, right? Well, we are interested in these three questions. First, from an empirical perspective, how are complex motion events expressed in this language? What is the distribution? And so a second question is a different one. It's more computational, it requires a computational analysis. Can we estimate the energy spent during the articulation of these complex motion events? So we are trying to find a way to estimate the energy use. And then our third question is, of course, age of acquisition related. Do native and late signers differ in terms of the energy that they use during production, right? Or the distribution? Do we observe any differences? And the stimuli is this. I'll give you few seconds to look at this. then we can continue. We first showed the manner to the participant. I know the ordering is not very intuitive here. It's the second one. We showed the participants the manner as in animation, as in videos. Then we asked them to produce the manner only. Then we showed them the path stimuli, combined both of them. And we asked the participants to, produce the manner that you saw in the animation with this exact path. So they produced, and the instructions were clear in that we asked the participants to produce both path and manner together, either conflated sequence, whatever, but they should include this information. So they all produced this described complex motion event. Our participants were 10 adult native signers, 6 females, 4 males. All participants were right-handed, so their dominant side was their right side. Deaf parents have deaf parents, exposed to it from birth, sorry, and the age range is this. Also, we had 10 adult late signers with this background information. All have hearing parents, they have delayed exposure to TIT, and all of them started learning TIT in a deaf school, basically. And the coding was as follows. We coded sequence, conflated, and mixed forms. So about the energy, like how did we actually try to calculate or estimate the energy use of the signer? So we use computer vision, and we use a Python library called OpenPose. And the first task was actually to extract, so this is a video, right? We recorded videos of the participants. And the first thing that we did is to, after we get the videos, we extracted 8 frames per second. So each second we extracted 8 different frames from the videos, and we applied computer vision on that. And then, so we get something like this output, as you see in the picture. So after we run OpenPose, on each frame, we get the coordinate information, right, of the joints that we select. We did this analysis for the left side of the signer and the right side of the signer. And after that, after we get the X and Y coordinate information on a 2D frame, we calculate the Euclidean distance of each joint, between the consecutive frames, and then we derived energy. And this is the formula, how we derive the energy. So basically, so there are 5 joints that we selected. There is the torso, as you can see. There are, fingers, shoulders, and goes on like this. There are 5 different joints that we are interested in. And so we have the joints, each joint, and we calculate the distance of the joint, initial joint, between this later joint in the other frame. So we calculate Euclidean difference, like how many pixels it moved, right? Basically, we are measuring movement, the movement of the joint. Then to normalize, we divide that to the movement of the entire sign, because the entire sign includes a lot of frames. So we have to divide that. And then we assign also weights to estimate energy, some concept of energy, right? So what is a weight? So, the idea is simple. If you move your torso like that, you will spend more energy. This is the idea. So we assign the torso 5x as the weight. We assign fingers just 1x, because moving your fingers may not require that much energy. So this is the idea, and we multiply that by the relative value of the joint. So some example videos. After we run OpenPose, we get something like this. Yeah. And so about our results, maybe I can talk about that here. So the first observation that we had was this. Late signers use conflated forms more than native signers. This was the first observation. So if you, dark blue one is the late signers, lighter blue is the native signer. So you see that there is quite a difference between native and late signers in the use of conflated forms. Late signers use more. And native signers, as opposed to late signers, use sequence form more often, which actually parallels ASL, right? ASL is reported to use more sequence forms. And we had 2 Poisson GLLMs, linear models, one with nativeness as a predictor, and the other without this predictor, to basically see which model is superior, which model is better, if nativeness can actually explain this data. Well, the model with nativeness as a predictor was fitted the data better, was a better fit for the data. And so interestingly, are energy results, right? Okay, so the energy spent on a complex motion event increased with late acquisition. So if you're a late signer, you use more energy in these complex motion events. This was one finding. Also, well, this is expected, but still cool. Using a sequence form also increases the energy because, sequencing includes two separate signs, right? So you, of course, spend more energy on that. Using the dominant side, so if you use your dominant side, use your more energy on that. We also saw that intuitively. But what about age of acquisition effects, right? For age of acquisition effects, we saw something interesting so that we saw an interaction. If a signer is a late acquirer, if a signer is a late signer, they use more energy on their left side of the body, so their non-dominant side. Again, if you're a late signer and if you use your non-dominant side, we found that you are using more energy compared to native signers. As you can see here, let me navigate you. So the first grid, let's say, is the left side of the body in the red rectangle. And the dark blue again is the late signers. And on the y-axis, you see the estimated energy, like pixel values with weights, like difference. And you see that late signers use, for each type of event, more energy on their left side, comparably more energy, interestingly. And this is our model. We fit in a mixed linear model to energy values, and these words are predictors. Nativeness, body dominance were entered as fixed effects, and participants and frames were entered as random effects. We also saw two-way interaction between nativeness and body dominance, as I mentioned earlier. So let's highlight a few of the effects. So you see in the non-dominant side, actually decreases the energy. You see this in the model. It decreases. It's a negative value. Conflation decreases energy, as expected. If you use simultaneous, you spend less energy. Sequencing increases it. And there is this interaction, which is highly statistically significant. If you're a late signer and you use your non-dominant side, you also spend more energy. And let's summarize all that. Late signers here in the study use more conflated forms, which was similar to Özgürek's findings with home signers. Native signers, as opposed to late signers, use more sequence forms. And we observed also, both native signers, interestingly, and late signers in this study use mixed forms to a similar degree, but they use mixed forms, both groups of signers. And we say here that although conflated forms decrease the use of energy, right, because remember, conflation decreases your energy, you don't spend much energy. In spite of that, and despite although late signers use more conflated forms, overall they use more energy. So there is this situation. And we also observe dominance, nativeness interaction. Late signers use more energy on their non-dominant side. And finally, I have a few implications. Maybe we can discuss that during the questions. Well, we say that sequential exponents could be the default strategy for natives, as observed for ASL, sign language of the Netherlands. Sequencing can be the default form for many sign languages, what signers prefer. And this is also similar to most spoken languages, English, Turkish, like some way of sequencing, pattern manner information. And conflation can be more iconic in nature, maybe easier to produce, these are all possible hypotheses. And age of sensitivity in complex motion event production, we provided some support of that. And so we said that late signers, when they use their non-dominant side, produce more energy, use more energy compared to native signers. So what could be the reason for that, right? And maybe one reason for that that we entertain here is maybe they inhibit their non-dominant side less frequently compared to native signers. So even though they don't have to move their left side, non-dominant side, during articulation, maybe they have problems with inhibition. This could be one way of explaining it. And also, I like the idea of reactive effort by Sanders and Napoli. So in this study, they say that, to move our muscles to produce a sign, we have some effort, right? We make some effort. But in addition to that, there is also something called reactive effort, that we have to sometimes make some of the muscles or joints passive during articulation. So they give this example of, if you do this, your torso is also moving, but your torso doesn't have to move, so you must keep your torso still, and this requires a reactive energy. So you must keep certain muscles and certain joints still, and this is also like some kind of an effort. Maybe late science could be having a problem with that, and like this is also very so there are not many studies using this methodology, and it could be interesting to have more studies looking at this more specifically. But thank you. And also, if you scan this QR code, you can access our repository on GitHub. So there is data code and our slides. You can play the cute dog video again if you access the slides. And also, there are some links. If you want to connect with me on Twitter or something, there are some links there. Thank you for
Wonderful. Thank you so much.